In your previous encounter of chemistry, you have probably discussed in detail the forces between atoms and molecules, those bonding forces which hold the atoms rigidly in place in a molecular subunit. Well, the molecules themselves can interact with each other, and in that case we have what's called intermolecular forces, the attraction and repulsion between those neighboring molecules. Now, these forces are much weaker than those bonding forces. So consider, for example, two water molecules. Now, in order to break the bond between the oxygen and the hydrogen atoms, we would need 460 kilojoules of energy per mole. But in order to pull apart the molecules, we would only need about 16 kilojoules per mole. So about an order of 20 difference between those two. It's these forces which allow for the formation of condensed phases, such as liquids and gases. Without those forces holding the molecules together, then they would just bounce off of each other and exist solely in the gas phase. Now, if we know something about the intermolecular forces, that's going to allow us to have some insight into the bulk properties of these substances. We can infer things like melting point and surface tension and solubility. Or if we know about those things, we can go the other direction and make some inferences about the types of molecular forces which are present. Now, these molecular forces exist in competition with thermal forces and thermal motion. So as the temperature increases, that's going to tend to override the intermolecular forces, but as the temperature decreases, those intermolecular forces are going to become more significant. So in the case that the intermolecular forces are much greater than the thermal forces, then that's where our molecules are going to be held together in a rigid lattice structure. That's where we have a solid. We could have the case where the intermolecular forces are about equal to the thermal forces. So now there's not enough thermal energy to actually separate the molecules and pull them apart. But what there is enough energy in order to give them some freedom of motion so that they can move around in adjacence to each other. Now finally, we have the case where we have much more thermal energy than is necessary to break those intermolecular forces. And so now the molecules are free to explore the confines of their container. They're not bound to each other at all, and they exist as a gas. So they can flow over each other as a fluid. It's a sparse fluid because they're all spread out, not bound to each other, and they take on the shape of their container. And notice that this increase of thermal force corresponds to an increase in temperature. And so we're familiar with things becoming solid as they freeze and becoming gases as they boil, depending on how much energy we've put into or extracted from the system. We're going to categorize these intermolecular forces as four major types. The first type we'll consider is London dispersion force. This was theorized by Fritz London in 1931, and this is the attraction between molecules due to what's called their instantaneous polarization. So frequently for molecules, they are neutral overall. So if we have two helium atoms here, they each have two protons carrying a +2 positive charge, and they have two electrons. Overall, that's a -2 negative charge, and it cancels out, so it's an uncharged atom. And two uncharged things are going to have no electric attraction to each other. But something changes if we bring these atoms very close together. Once the helium atoms become very near, then the electrons can start to spend more time where they would like to be between these two positively charged nuclei. It's favorable for them. Now, when these electrons spend more time in that area, then the other electrons can no longer occupy that area, so they're excluded out here. And so what we have a more or less fixed negative charge and fixed positive charge. That's a dipole. And we again have a dipole. And these two dipoles have attraction to each other. And this is what the force that allows these substances to form liquids. As you lower their temperature, then eventually their thermal motion becomes overcome by this dipole attraction, and so the gas will condense into a liquid. And this effect will be augmented if we have more positive and negative charges. So if we have more protons and more electrons, so this larger atom is going to polarize more than our helium atom is going to. And what that means, since the number of electrons is roughly going to increase as the molecular weight increases and we have more protons, that means that the polarizability of the molecule is also going to tend to increase with the molecular weight, and that's going to lead to stronger intermolecular forces. As evidence of this, consider the boiling temperatures of the noble gases. So helium starts out and it transitions between liquid and gas at 4.2 kelvins and has a molecular weight of just 4 grams per mole. And as we increase up to the 131 grams per mole of xenon, we also increase into a boiling temperature of 165 kelvins. And this is because the attraction between these xenons is increasing. So we have more electrons and protons, more opportunity to form a stronger dipole. And so it's going to take a larger temperature in order to overcome those forces and pull apart the atoms to form the gas. The shape of these molecules is also important in determining the total amount of London dispersion force they experience in their interactions. So if we have linear molecules, then these will tend to have a significant overlap, significant number of places where the polarization occurs of the electrons in the atomic nuclei. And so they'll have lots of attraction, and therefore they'll stick together more compared to if you have the branched molecule, then even though it might be the same molecular weight and have the same total number of electrons and protons as this linear molecule, only a fraction of those are going to be able to get close enough to experience London dispersion forces. This is one of the major factors determining whether or not your fat is a liquid, such as olive oil or vegetable oil, or if it's a solid, such as butter. And if you want your fat to be a liquid, then what you can do is you can put kinks in the chain of the molecule called points of unsaturation, and then your molecule will have less overlap, so it'll have less molecular force between the molecules, and so it will be more likely to be a liquid at room temperature. Next major category of intermolecular force is dipole-dipole forces. This is when we have molecules with permanent dipoles. An example of something with a permanent dipole is hydrofluoric acid. So fluorine is very electronegative, hydrogen is very electropositive in comparison. Together we have a polar covalent bond with an overall dipole for the molecule. And so when we bring these molecules together in a liquid, the dipoles will tend to align, leading to increased attraction between these molecules. Now this attraction is going to increase with the polarity of the molecules. So we have relatively strong attractions here since hydrogen fluoride has a fairly polar bond. There's an important case in our dipole-dipole interactions. That important case is when we have hydrogen bonding. So this is where our dipole-dipole interaction involves hydrogen in a polar bond. This is typically with fluorine, oxygen, or nitrogen because those are very electronegative atoms, so they give us very polar bonds. And this dipole is going to associate with a lone pair of electrons on an electronegative atom in the other molecule. So an example of this would be water, H2O. So it has two lone pairs of electrons, and it has two hydrogens in this dipole with oxygen. And so it can actually associate with four other water molecules. So form four hydrogen bonds. Now, hydrogen bonds tend to be stronger than regular dipole-dipole interactions. There are a couple reasons for that. One reason is because hydrogen is essentially just a proton. Doesn't have any shells of electrons, which would prevent it from exposing this full positive charge here to this electronegative oxygen. And because it's so small, just being this lone proton, it can get in very close to that atom that it's attracted to. And so that's what makes these hydrogen bonds special and particularly strong as far as dipole-dipole interactions go. And this leads to some important properties of water. For example, it has a very high boiling point for such a small molecule, since it has such strong interactions. Now, an important note, hydrogen bonding is not just because you see hydrogen present. It must be part of this dipole here, and it must also be associating with these pairs of electrons. If you have something like CH4, which is methane, then that is not going to give you hydrogen bonds. First of all, carbon and hydrogen have very similar polarity, so there's no dipole there. There's also no pairs of electrons floating around for the hydrogen to associate with. So in this case, there's no hydrogen bonding. In this case, there is. So you have to pay attention to what hydrogen is attached to and whether there are any of these lone pairs available. The presence of all these hydrogen bonds gives water a number of unusual properties as a molecule. In addition to the very high boiling point, it has a very high viscosity. It also has a very unusual feature, which is that its solid is less dense than its liquid form. And so when water cools down, it will tend to arrange itself to maximize the amount of hydrogen bonding which occurs, which leads to this very space-filled structure here. And you can tell that's much less dense than when we have the more disordered arrangement of water molecules. Environmentally, it's very important because that means that lakes tend to freeze from top to bottom instead of bottom to top, and ice acts as an insulator, which winds up preventing the entire lake from freezing, which would be a more difficult environmental hurdle for fish to deal with than just having a layer of ice on top of the pond. Our third form of intermolecular force is ion-dipole forces. When you have molecules with permanent dipoles, such as water, it's partially negative oxygen and it's partially positive hydrogen. These will associate with ions, which have permanent electrical charges. So the negative oxygen will tend to associate with that positive sodium. And this is very important in the dissolution of salts in polar substances, such as water and alcohol. Our fourth and final major category is ionic forces. So these are attractions between charged ions. So usually these form a network. So we have a repeating network of positive sodiums and negative chlorines for sodium chloride. This is definitely the strongest intermolecular force. And overall, ionic forces are going to be much stronger than any of the other forces. But next in line is ion-dipole interactions. Then our dipole-dipole interactions, of which hydrogen bonding is a special category, and it's stronger than the typical dipole-dipole interaction. And all these are greater than London dispersion forces, which are our weakest force. However, London dispersion forces make up the majority of intermolecular forces simply because they are so common compared to these other forces. And so as an example, let's see if we can list the intermolecular forces between H3COH molecules. So the first thing that we're going to need to do is we're going to need to figure out if we have any dipoles present. We know this is not ionic, it doesn't have any charge on it. And we can take London dispersion forces as a given. Those are always present for molecular interactions. So what remains is to figure out if we have any dipole-dipole interactions, including hydrogen bonding. And we're not going to have any ion-dipole bonds, since we don't have any ions present. All right, so the first thing we have to do is we need to figure out our structure. So we'll start with the Lewis structure. So we have carbon with 3 hydrogens attached to it, attached to oxygen, attached to hydrogen. And if I count my electrons for all of these, I should have 14 electrons total. So I can put the last 4 electrons on that oxygen. And I'm going to have some bond dipoles here, because oxygen is much more electronegative than hydrogen or carbon. So I have some bond dipoles like that. And carbon and hydrogen, they have similar electronegativity, so there's no polarity there, no dipoles present. Now we have to figure out, in the actual three-dimensional molecule, if we continue to have a dipole, or if these cancel out. So what I would do is I would look up my geometry for a central atom with 4 things bonded to it. And then here I have another central atom with 4 things bonded to it. This pair of electrons, this pair of electrons, this pair of electrons, and this pair of electrons. In this case, it has a different molecular geometry because we don't include these electrons in the molecular geometry. But in both cases, this is tetrahedral, and just the molecular component is going to be bent. So let's go ahead and draw that. So I have my tetrahedron with carbon at the center. For my convenience, I'll go ahead and make sure this oxygen bond is in the plane of the paper. Right now I have another hydrogen, my final hydrogen. Now I'll go ahead and work on the next piece of this molecule. Now since this is tetrahedral geometry here, I'm going to have 109.5 degree bond angle on that oxygen. I'll do my best to draw that. If you wanted to be explicit, you could put in these lone pairs, which are what's causing that bond angle. Now I have my hydrogen here. So now my bond dipoles, I have that dipole, I have that dipole. The total effect is going to be, both of these are pulling up, but one's pulling left and one's pulling right. So overall, my net dipole is going to be something like that. Now it is going to be shifted just a little bit in one direction versus another direction because carbon and hydrogen don't have the same electronegativity. But this is a good enough indication of the dipole. So this is the dipole for the molecule. Since the molecule does have a dipole, that means that we're going to have dipole-dipole interactions. When we have 2 of these molecules next to each other, we're going to have the possibility of the hydrogen from one molecule associating with the lone pair of electrons on this other molecule. And since it's part of a polar bond and it gets to associate with these lone pairs, that makes this a hydrogen bond that can form here. So our molecular forces that we have for this molecule so we had London dispersion forces as a given. There are no permanent charges, so there's neither ionic forces nor ion-dipole forces. We do have dipoles which can interact with each other. So we should have dipole-dipole interactions. And in this case, we have a special kind of dipole-dipole interactions. We have our hydrogen bonding, which tends to be stronger in general than normal dipole-dipole interactions. So those are our forces for this molecule. And because we do have some of these stronger forces, the hydrogen bonding, which is rather stronger than the London dispersion force, then for instance, that would lead us to conclude this molecule is more likely to be a liquid at room temperature than a gas, even though it's a small molecule. We might conclude that it's going to have a higher viscosity. Analyzing the presence of these intermolecular forces gives us some insight into the nature of the substance.